In this video, we're going to choose the best airfoil for the flying wings airplane or tailless airplanes. So we study approximately 50 different airfoils designed for this purpose. We're going to create this software which is going to plot each airfoil on the feature space, and then we can choose the ones which are the best performing airfoils. As a result, I'm going to see this beautiful graph. So this is the feature space, and on this feature space all the airfoils are plotted. So those airfoils, 50 of them designed for the flying wings, are plotted. So this feature space consists from two axes. So the first axis is the minimum drag coefficient for the high speed, and the y-axis is the maximum lift coefficient for the low speed. So the objective is to fly fast, efficiently fly at the high speed, and to have high lift coefficient at low speed, or fly as slow as possible. So this software was created. Not a software, it's just a Python script. Very simple. Here you can choose the airfoil that you like. So here's the airfoil, and here's the position of this airfoil on this feature space graph. And here's the profile itself, and the graphs for the polygraphs for lift and drag coefficients and for the momentum coefficient. So if I choose something else, let's say PW51, it's close to the minimum drag coefficient, so it's a different profile, it has different curves. So I cannot fit all, maybe I can. So now you can see all the graphs at the same time. Boom. So you have the different position on this curve, and you have so now we have position somewhere there, and we have this airfoil and the corresponding graphs. Okay, this feature space, or this graph, actually allows us to see visually which airfoil performs well. Obviously, we would like to have the minimum drag coefficient, so we would like to have airfoil somewhere there, and we would like to have the maximum lift coefficient. So in this area we would like to have the airfoil. And if you look at this graph, what we can conclude that among those, actually not a simple airfoils, those were specifically designed for the flying wings or tailless airplanes, and those airfoils are performing well, because I haven't included the airfoils with the battery view. So here's the best ones, except maybe few. And if you look at this graph, you will see that most of the people get the design right. So we see like most of those airfoils placed here, and that's exactly where we like to have those airfoils, to have them small drag coefficient at high speed and to have maximum lift coefficient. Okay, so this is the result. I'm going to talk about this result later, but first I would like to discuss steps which actually allow us to plot this beautiful graph. Before start the simulation, we should answer a few questions. The first remark is that there is no perfect airfoil, but there is the best airfoil for the given operational range. So we have to choose the operational range. And let's say we have a wish to fly at this speed, and for the plane to have the minimum drag at this speed. So to fly efficiency at this high speed, we have to have the airfoil having the minimum drag at this speed. So that's simple requirement. The second requirement is what is the lift. We should ask what is the lift coefficient. And if we plug the numbers, so the lift coefficient equation for the lift coefficient was described in my previous video. So if you plug the numbers inside, and the numbers are those. So mass is 1 kilograms and wing area is 0.1 meters squared. If you plug the numbers, you will get the very small lift coefficient. So the lift coefficient is not going to be the limiting factor. Almost anything can produce this lift coefficient. at this high speed. Okay, so the second question is what is the drag needed for the plane to be able to fly at this high speed? The drag equation is this, again described in my previous video, and this equation includes the drag coefficient. The drag coefficient is unknown. You know the lift coefficient, so we can choose the drag coefficient corresponding to this lift coefficient. To be able to do it, we have to plot the polar graphs at given speed, so we have the 80 meters per second speed, so we can compute the Reynolds number, and then plot the polar graph for this Reynolds number. So the Reynolds number is corresponding to this speed. So after plotting this curve, we can look up a lift coefficient, so 0.025. So you look at the y-axis and you pick the corresponding drag coefficient, then you go down and you find the drag coefficient. And drag coefficient is 0.005. And let's say we have the worst condition, terrible airfoil, so we double the drag coefficient. So for this drag coefficient for the Q, dynamical pressure for the wing area, we can plug the numbers in, and we receive that we would like to have, we have to have speed equivalent to 4 newtons. 4 newtons, this is approximately 400 grams. So this, once again, totally achievable, but not terribly high thrust. It can be done. So the first requirement to have this speed is it can be totally fulfilled if we have the drag coefficient equivalent to 0.01. Okay. Now the second requirement. The second requirement is to have a slow speed as possible. And to have a small speed, we would have to have very high lift coefficient. So the higher the lift coefficient, the slower the speed can be. Because once again, if we increase the speed, so the lift coefficient can be very small. So the higher the speed, the smaller the lift coefficient. But if the speed is small, then the lift coefficient is going to be significant, meaning that we would have to have a high alpha. And now imagine flying plane with high alpha. Probably the drag is going to be significant as well. So we have to check if we can have this drag. We know the power of our motor. So the motor has this power. This power is sufficient to fly at high speed, 80 meters per second. So we know the thrust, which is 4 Newton, and we know that we're going to have high lift coefficient at small speed. So we go here and we plug the number once again. For the drag coefficient, we divide the thrust by the QS, and QS is known. Speed is slow, let's say 10 meters per second. This is the wing area. You plug the number and you get the drag coefficient. Limit for the drag coefficient is 0.65. So meaning that if we plot this line on the drag axis like this, let's say, everything that is in the left half space is okay. But if we have drag exceeding this number, 0.65, then the motor does not have sufficient thrust for the propulsion of this plane. Okay, and the final step is to find the Reynolds number for the simulation. So we use this equation. In my previous video I was talking about this, and we just plug the number. So we have the chord length, assume we have the chord 0.1 meter, and the speed, we know the speed, so that we wish 80 meters per second and 10 meters per seconds. If we plug this number, we get the two Reynolds number for the simulation. But first, let's choose the airfoils for the simulation. The first step is to find airfoils, and internet can be useful for this purpose. So here is the web page. It's a German web page, and on this page they have different airfoils for the S wings, wings with S profile, or tailless wings. So this is the one source. Here's another source. So the page is here, I will leave the reference below. So what this page is good, it has a description of airfoils, of its performance, has some characteristics available and so on. But what I have done, I just basically read the conclusions. Oh yes, it's a web page in German, so the Google translator is helpful. So I translate this web page and then I can read information. So you read the conclusion and you see if profile is any good. If yes, then you can download it and store it for the future use. So that's what I did, and I have the collection of those profiles. So I have many of them, and if you look inside, you will see that the data is like this. This is the good one. But unfortunately, when you gain profiles from different sources, sometimes they have mistakes and they have some inconsistencies. So what you should do, you probably should use Python. So here is the Python. Python script. So what I did, I just plot this profile out of the file. So it's a very simple function. So what you do, you define the parameters you need, and then you basically read the text file into data structure, which is basically a matrix. So very useful function. You can write it yourself, but why not to use this function? And then what you can do, you can plot the information from this file. So this is the Airfoil. So if you look at the file, what we have inside, we have X and Y. So this is X and this is Y columns. And what you do, you just plot Y over X and you get this beautiful curve. But it's not sufficient, because for simulation we need a file of particular structure. So here is the structure of the file. So what you should have X starting from 1 and Y is corresponding to X, and then you go back to 0 and then you go back to 1. So Y is negative. So you have to have this structure, and sometimes in files they have different structure, different numbering and so on, some mistakes. So it's very helpful to just plot this airfoil. And for instance here, so if you look at the X is blue, X is red. So X is red, so it starts from 1, start from here, goes to 0, 0 is here, and then go back to 1. So this is the X, and blue is corresponding Y. So it starts from 0, so starts at 0 here, then it's positive, and then it's become negative, and go back to 0. So this is the file structure you're looking for, and that's why what you can do, you can plot all the files that you have. And here is the script for this. So basically what I do plot this in a loop from the given directory. So I just scan all the files from the directory and then plot them all. So I'm plotting the airfoils from this folder. And this folder has all the airfoils that is available on this web page, plus few airfoils from RC groups and some other airfoils. So I choose basically the one with the good reviews from here, and got some other airfoils with good reviews as well. So after that, once we have it, we can plot them all from the directory. So I do that, and then I have the result of all the airfoils in this folder. And you can look at them visually and see if there's some problems inside. If there's some issues with those airfoils. And actually I had maybe 5 bad apples in this folder, so I had to fix it. Again, I fix it with Python. It's very easy to rearrange the data. Maybe sometimes I have to look inside and do it manually. There's some issue with the encoding and so on. So after that, I have all the airfoils clean and available for the future simulation. And to run the simulation, we have two options. The first one is to use Xfoil and write batch script in Python to scan all the airfoils that we have. And the second option, use the ready solution, XFL R5 software. And this software we can run the simulation for all the airfoils in one click, basically. So we choose File, Open. Here is the airfoils that we have. Then we open those airfoils. And to see the result, we go to the direct foil design. And here is all the airfoils that we have. For instance, you can look, for instance, see particular airfoil by clicking on the style, changing the color to red, and make it line more visible. Line width is higher, a bit thicker line. Okay, so this is the airfoil, this particular one, zip kill, and yes. So now we're back to the. Now we're ready for the simulation. We go to the Xfoil direct analysis, and then we choose analysis and multi-threaded batch analysis. Select this option. Edit Reynolds number, so I have done this previously. So what we have here, we have two Reynolds number, 50,000 for low speed and 550,000 for the high speed. And one thing to notice that we have to use higher Reynolds number for the higher and critical number for the low Reynolds number, because we have seen this from the practice in the previous video when I was using wing tunnel data. So here is the results. So here is the wing tunnel data. So the red is the wing tunnel data for particular airfoil. This airfoil. So I have data from the wing tunnel, and then I have simulation data from Xfoil, the blue line. So if you have a critical equivalent to 11, you have good correspondence. But if you have a small critical number, then what you see is this curve. Oop. So the blue line corresponded to Xfoil results, different from the wind tunnel data. So in other words, we have to make in simulation, we have to make simulation kind of more turbulent to actually pick up this drag increase. So to see this drag increase, you have to make it add more turbulence to the air. So increase critical number, and then you have similar results. So that's why you have 11 for the low Reynolds number. Now press OK. Also what we do, we go to the advanced settings and we choose the number of iteration. By default, I found that the number is a bit too low because sometimes you do not have convergence. So if you put 500, it's sufficient. But sometimes it's going to be it's going to take a bit longer. Okay. Now what you do, you choose the airfoils. So you select all airfoils you have loaded. So you select all of them. Press OK. So you see the list of airfoils ready for the simulation. And the final thing is to choose the alpha range. So for the high speed, I'm going to use a small range. I think 2 degrees is going to be sufficient for the high speed. I'm going to make small steps. 001, 002. Okay. And yes, so we have to change this because I'm going to use different range of alphas for the low and high speed. So I don't need low speed at this moment. I will remove this. Okay, so I have only the high speed with critical number 9, and I also have the range for those airfoils. Just make sure that I have all the list. Yes, I have all the list. And now we are ready to run the analysis. So it goes pretty fast, because usually there is no problem with high Reynolds number. The low Reynolds number actually the one that gives you the problem, especially for the high lift, for the high alpha. Well, this one has some issues, I think, but because we have the number of iteration high, 500, so we do actually have solution, even for those which take a longer to simulate. And we have the analysis complete. So we close it and we see the result. And we have to do it once again, because some graphs are not starting from zero, meaning that they have positive lift at negative angles of attack. So we have to change the range to include negative alphas. And also we can reduce the range for the alpha, maybe not to 2 degrees but less, because the coefficient that we need is 0.025, and here we have pretty high coefficients. So we choose the negative alpha to make sure we're going to capture the lift coefficient, small lift coefficient, and we're ready for the analysis. And it's done. Okay, so now it makes more sense. Huge negative drag. So for the negative lift coefficient we have huge drag, but that's okay. All we need is a curve which is approaching the 0 point here. So you have to choose the best one. But okay, so this is done. So now we're going to save the data, because it's kind of difficult to choose the best position on the best curve, the best airfoil. So we're going to use it. We're going to use Python. And now let's save all the information. Polars, export all, text format. And now we're going to choose the folder. Okay, so yes, it's present. So the information is here. So you can look at the folder 150K, and here's the information. So we have alpha, we have lift coefficient, drag coefficient, and so on. So all is good. So now we're ready for the next step. So we're going to simulate for the low Reynolds number. And here is the low Reynolds number with critical number 11. And the range for the alpha is from -3 to 12. And let's run analysis. Well, this is going to take a bit longer, I think, because we have a high range, but at the same time a bit less point. And we have the results. So if you look, there is no error messages. It's kind of amazing. So no mistakes. Okay, close. And here is the curves. Oh, this is expected actually. So we have huge drag happening for some of the airfoils. And the lift, we have pretty good airfoils with sufficient lift, close to 1. Okay, so now we're ready for the. Have to save the data once again. Polar export text file, and we choose the folder. So 50K. Okay, so once again, it's not easy to kind of select the right airfoil, because first of all we have to add the wing effect for the low Reynolds number and high alphas, and secondly we have to look at which curve is actually the best. So we're going to use Python, and let's do it. And this is done. I have those beautiful graphs plotted with this simple code. So what this code does, it goes through the files in the directory and extract information from the text file to the matrix with this function and then we can select different vectors that we need and plot the result. So I will show the files. So this is the result of the simulation with Xfoil, and inside we have this information. So different columns, and in each column we have the value at a particular alpha. So we have different alphas and we have different values for the different coefficients. So we have plenty of those files, and we have scanned all of them, and as a result we obtain those graphs. So lift coefficient versus drag coefficient for each airfoil that we have simulated. Okay, one remark is here that this is not just foil, but we also have the wing effect added. So we have used this simple equation, basically induced drag, which is proportional to the square of the lift coefficient. And we have seen that this simple equation has almost identical result for as the simulation with different methods. For instance, here. So here is the result for the analytical equation that we can use, and the result is compared to the simulation with the XFLR5 software. So the few methods can be used for the exact solution. For instance, this method, but the result, which is very simple, result obtained by this simple equation, has very good correspondence. So there is no need to use the software. You can just use the simple equation, and thus with this simple equation we can add the wing effect for result. And for the convenience, I can put the results in a separate file, so here, and I can see different simulation I have run. For instance, here we have the simulation for the foils, airfoils. So there is no wing effect simulated at a low Reynolds number. Then we have added the wing with aspect ratio 10, and you kind of can see how those curves become more tilted. So meaning that they have more drag. So induced drag from the wing is affecting the airfoil curves. Okay, so this simulation was done with uncritical 9, but as we have seen from the wing tunnel data, so here's the wing tunnel data, that sometimes you have to have uncritical 11, especially for the low Reynolds number. So to make a good fit between the data from the wind tunnel, the red lines, and the foil, the simulated foil, the blue line, you would have to increase the critical number to 11. So on this graph I have the airfoils plus wing effect computed at critical number equivalent to 11 and the low Reynolds number 50K. So here is the graph without, here's the graph with critical 9, here's the graph with uncritical 11. Okay, simple. Next, let's run simulation for the airfoils at higher Reynolds number. So in this case I have 550K Reynolds number and critical number is 9. For the high Reynolds number simulation, you don't have to increase the critical number. I found that this number is performing well. So we have those curves, kind of looks a bit strange, but if we're going to add wing, it looks more kind of usual. But have to add one comment, and that we actually need lift coefficient, as we remember, 0.025. So 10 times less somewhere here. So we need very small lift coefficient, and for the small lift coefficient, the wing effect has zero effect. So there is no wing effect for the small lift coefficients because the induced drag produced by the wing is proportional to the lift coefficient squared. And if you have this small number, so it's going to be almost, well, not almost, but completely negligible. So we can ignore the wing, but if you would like to see kind of a broader range, what's going to happen at high speed and high alpha, you can plot a bit more information, and then you're going to see those graphs. Okay, so once we have those curves, that's all we need, because we have the lift coefficient versus drag computed at low and high Reynolds number. So what we can do, we can choose, for instance, so here is the low Reynolds number, so we have 50k. 50k Reynolds number is approximately 10 meters per second speed. So what we need for the low speed, we need high lift coefficient. So we go here and we pick the top point from each curve, which is the maximum lift coefficient, and we want to make sure that we stay in the range of the maximum drag coefficient we can have. From the previous section, you have seen that the maximum drag that allowed for this motor is 0.6. In this case, is 0.2. So it's not a limiting factor at all. So you just pick the maximum point for each curve to get the maximum lift coefficient at low speed. If the motor is not as powerful, we have less thrust, then we might have the maximum drag coefficient somewhere here or somewhere there. Depends on the situation. So in that case, you would have to pick the maximum position in this range, below the maximum drag coefficient limit. Okay, so this is the point number 1, and the point number 2 is at high Reynolds number, and we know that we have to pick the minimum drag. So we look here and we choose the point which has the minimum value. So the point at which we have the minimum drag, we need to choose the point on each curve. So as a result, we're going to have 2 points, so x and y, and we can plot those points on this graph. So on x-axis, we have minimum drag coefficient. So from here, minimum drag coefficient, and on that axis, on y-axis, we have the maximum lift coefficient that we have chosen. So we have pairs of x and y, and we can put each point corresponding to each curve. So each curve can be represented by this point from the point of view of usefulness for our purpose. So, and we know that we would like to have a small drag as possible, so we go here. So this is the drag at the high Reynolds number at high speed, and this is the minimum point for each curve. So we would like to have the curves in this range. So minimum drag, small scale. So somewhere here. And for the maximum lift at the small Reynolds number, we would like to have the points somewhere there. So after working with this code a bit, I added the names for each point, so done automatically, and I can also choose the desired airfoil from here, and I get the corresponding point on this feature space, and we're going to see actually where it's located, which is the minimum drag for this airfoil, and what is the maximum lift for this airfoil. So okay, so this was done. So I completed this code. Maybe I'll show it once again. So we have seen this code in the beginning of the video. So this is the code. So I can choose the, let's say, Clark YS airfoil, well known, sometimes used. So here's the point. So Clark YS is the worst possible airfoil you can have. Has a very small lift at small Reynolds number and have a very huge drag at high Reynolds number. Well, at least for the Reynolds number of our interest, it might be perfect airfoil for some other Reynolds number. I think it's designed for the high Reynolds number, but if you use it for the plain design, the specification we have described, then you're going to have the very bad performance of this particular airfoil. So I also can plot the profile of this airfoil and polars for drag and lift coefficient and small Reynolds number and corresponding momentum curve for the small Reynolds number, as well as I can do the same for the high Reynolds number. So this was done, Let's choose something else just to see how it works. Well, let's say this is not bad. TL54. I think it's Tailless 54 something. Boom. So it's here. Not the best option. 55. Oh, okay. So TL55 has a small drag and has okay lift, 0.85 I think. Okay, so we have this code, we have plotted those curves, and next step is actually to look at the results. And we can do it by looking at this graph once again. So in this section we have the best performing airfoils, and in that section we have huge drag and small lift. So those are the worst airfoils. So we can segment this feature space in two regions. So the first region is the best airfoil, the second one is the worst. And can look, basically we can plot introducing the limits for each coefficient, and then we're going to see, for instance, the best airfoils and the worst performing airfoils. And here's the best airfoils. Ta-da! So those are good performing airfoils. And from the point of view having minimum drag coefficient and maximum lift coefficient, those airfoils are performing very well. So they all a good choice, and they kind of not very different from each other. If you look at the percentage, so the absolute value are kind of a bit confusing, but the percentage is maybe 12%, 15% difference, 15-20%. So you have 20% on this scale and 10% on and 15% on this scale. So they all good choice, not like a big difference. And it's also good to see that many of those airfoils are well known. For instance, this TL55 or MH45, 60. For instance, you can read the RC groups form. You will find that this airfoil PW51 is advised airfoil, and PW51 is placed here. So it has small lift, has small drag coefficient and sufficient lift, 0.85. So this is a good choice. And we have many other airfoils, and I recognize many by the name. And it's also good to know that, for instance, on this big picture, if you look, you'll see that many of the airfoils are actually placed in the right place. So people have the design right, and those airfoils, most of them have small drag coefficient and high lift coefficient. Okay, but we also have bad apples. So we can go here and know that we have bad performing airfoils. Those are the bad apples. For instance, Clark OS is the worst performing airfoil. So many people advise to use this airfoil, but it's the worst option. I think because it was designed for the high Reynolds number, so it's not supposed to be used for small planes or small Reynolds number. Second bad performing airfoil is FunJet. FunJet is I found it on the internet. Someone captured airfoil from the model, so there might be some mistakes in the capturing process, or maybe the model itself was not designed well. Well, it's not going to be like terrible, but maybe 2 times. You can find 2 times better airfoil than that one, but it's going to fly anyways. So there are also some airfoils here. So what I did, I look up the German webpage, this one. For instance, if you look here, like I can look up, let's say this airfoil, HS6. So we go on this German webpage, translate it, and here's the airfoil, and here's the description. So unfortunately, conclusions are incorrect. Hardcore speed profile for boards. So this airfoil is not high-speed airfoil, so it has significant drag. So maybe, like if you read the description or the conclusions, you'll find that this airfoil probably has some historical value for this person. So we can long time ago, but it's not the airfoil you would like to use for the high speed. So don't listen to anyone and make your own conclusions. Run the simulation and find out by yourself what is a good airfoil and what is not, because sometimes you might read some good reviews, but in the reality, like for instance Clark OS, it's terrible. Airfoil or HS6 is better airfoil. But people have good reviews about those airfoils because they have been using those airfoils or whatever other reason. So this one thing, and the second thing is that actually most of the reviews, most of the comments are actually correct, because if you look here, the good airfoils, many of those airfoils have good reviews. So I think that maybe on average people are right about things, but sometimes they have some wrong conclusions.